this session worth your while, and hopefully you won't regret making this your first choice for a reInvent session. So it's added pressure. I haven't had my coffee, so whatever I say over the next hour, I don't take responsibility for it. I see a lot of coffee mugs, so that's great. So let's talk about what we'll be covering over the next hour or so. We'll start by just a quick overview of where we've come from when it comes to data processing, how it has evolved. Just a very brief, very interesting overview. We'll talk about what modern business needs are when it comes to sort of data and data processing requirements. We'll touch on which tools are best to use. Naturally, the topic gives it away a little bit, but we'll talk about batch and streaming both, and which one you can use when. And then Sophie will take you through an example of some sample architecture of how you can convert your existing batch systems to modernize them and use them as stream processing systems to achieve the goals that your businesses might have. And we'll end it with some takeaways so that you're able to sort of take all this and synthesize it before you leave the room, hopefully. So without further ado, let's dive in. We'll talk about the evolution of data processing very quickly. As I said, touch upon it a few seconds. Human beings and businesses have collected data for thousands of years. You can actually look up, and interestingly, some of the earliest records of record keeping date back to 3,000 years in ancient Mesopotamia. And it started with like clay tablets, literally. Business was slow. You sort of like did your business from 9 to 5, and you collected some data, and then you were able to like make these beautiful inscriptions on these clay tablets. But then as modern businesses evolved, more and more data started getting produced as business activity sort of grew, as population grew, and we went from sort of clay tablets to sort of ink on paper in form of ledgers and notebooks, and then bits and bytes in the 20th century. And data production as well as data analysis and processing has just exploded. And that leads us to modern data landscape. Data processing in the 21st century has come a long way from where it was from our predecessors. The ubiquity of the internet, the advent of the smartphone, e-commerce have made businesses go online, and data production has become a round-the-clock, 365 days a year kind of thing. And you have data being produced, data coming from actually diverse sources, which are new and unique in nature. So there's no like structure always that data has. It may come from, it may arrive in multimodal formats. And as a result, you have to contend with diverse data when you're thinking about processing it. Data is also being produced continuously. We talked about how businesses have evolved to being much more 24/7, much more available. Shopping activity, business activity isn't contained to like sort of working hours only. It's happening around the clock. It's happening all across the globe. So data is being produced continuously. And interestingly, data is also being analyzed by many applications. More and more applications within your business, and I'm sure you all can relate to it, are greedy to get their hands on the latest information, which is captured by these interactions that customers have with your businesses or your internal processes have with your businesses. And as a result, all these applications need access to this data. So the data is also being analyzed by many applications. Let's also now take a moment to understand what businesses require from this data. Naturally, businesses are becoming more and more data-driven. Organizations are becoming more and more data-driven. And that has led to an evolution of how business needs have shaped over the years. Some needs have persisted the test of time. So all businesses continue to require reporting, whether it's weekly reporting, daily reporting, monthly reporting. Execs need those reporting to spot sort of longer-term trends and set their strategy accordingly. And that continues to be a strong pillar of business requirements when it comes to data. But there are a couple of other ones as well that have started taking shape in the past 10 years or so. First is the ability to generate not just insight, but also faster insight. And this is done with the idea of insight leads to better decision-making and faster decision-making. Think of a business that's producing customer interaction data. Would you rather process it right away, or would you process it 2 days later or 3 days later or the next day? And then last but not the least, artificial intelligence and machine learning have become strong pillars of the modern business data strategy. And increasingly, your differentiation through artificial intelligence, through machine learning models, is reliant on the quality of your data and your ability to process it. So if you look at, sort of take a step back and look at what businesses need their data to do, it continues to need the data to power business reporting and BI tools, but it also requires data teams to be able to make data available for business teams to generate faster insights, as well as power machine learning and artificial intelligence capabilities that can set the stage for differentiation in the years to come for your companies. So when you put these two things together, which is the modern data landscape and its evolution into sort of continuous data processing and diverse data processing, and put it against the modern needs of a data-driven business, which is the ability to generate faster insights, continue to power BI tools, but then also power my generative, artificial intelligence and machine learning capabilities, including generative AI. We realize that maybe the tools that we've been using so far, or we at least have to ask ourselves, the tools that we've been using so far, are they good enough? So we'll evaluate both of those tools next, very quickly. So the first one is obviously batch processing, and this is at a high level, just the ability to take a snapshot of your data at fixed intervals of time and process it to deliver some kind of information to downstream systems, whether it's applications or dashboards or even reporting. And batch processing is great. It works for a variety of use cases and continues to have its place in business. As we talked about, powering business reporting and BI tools, which happens sort of at a fixed cadence every hour, every day, or every week, continues to be well served by batch processing. But what about the other two pillars that we sort of talked about? The ability to generate faster insights, and then also the ability to power your artificial intelligence and machine learning tools or capabilities. We'll demonstrate this with an example of, with a sort of a commonplace high-level example of a factory that is trying to monitor sensor readings and using it to detect proactively any sort of issue or any sort of problem within its installed equipment. So we'll take an example of, let's say, 4 motors producing a bunch of readings from those motors. Beg your pardon. Bunch of motors producing readings through sensors such as temperature, vibration, speed, et cetera. And this data is available for you to collect and process. Now, if you were to implement this or use a batch reporting system or batch processing system to collect, aggregate, and process this data, you would do something like this, where you take a snapshot every hour at the top of the hour and process them in these batches. Now, let's assume your maintenance manager comes to you and says, I need this data to be able to detect defects. And my goal is to, actually, let me take a step back. So in a batch system, you would collect this data in a localized database somewhere, take a snapshot, and then at every hour, you'd send it to a downstream database where any of your querying tools can be used or dashboarding tools can be used to highlight what the readings are. Now, let's say if you're using this system to do defect detection, as I said, in the case of your maintenance manager wanting to proactively identify issues with a particular machine and wanting to maintain it in real time, let's see how this would go. Your goal, again, is to generate that insight for your maintenance manager to be able to detect defect and proactively mitigate it. Let's say there's a machine that produces an out-of-band reading at time t equals to 1. Your system would ingest it after a few seconds of latency, just standard network latency, and that data is ingested at time t equals to 2. Now, your batch has been running for a while, because as we talked about, you're taking a snapshot every hour. Let's say your data ingested sort of right after the previous batch was done, so there's still like 50 odd minutes for you to run the next batch. You run the next batch at time t equals to 3. That is when the processing starts, and the processing takes a few seconds to a few minutes, depending on the size of the batch, and at time t equals to 4, which is almost about 16 plus minutes away, is when the data will be available. Now imagine a scenario where your maintenance manager's goal is to be able to detect this defect and proactively mitigate it. Would they be happy with this result? I don't think so. So I think it's safe to say that batch processing isn't sufficient to produce faster insights. What about artificial intelligence? Let's take another example, and this one probably hits closer to home for a few of us. Chatbots are becoming ubiquitous with the advent of modern generative AI, and let's say you work for an online travel agency. And you're tasked to build a travel chatbot because you want your users to be able to find traveling information like flights, hotels, car rentals much more easily. In this situation, let's say you have a chatbot which provides a querying interface to a bunch of users. And at the back end, this chatbot is powered by a large language model, which is able to interpret these queries and provide those answers. But then you also need context because you need flight price information, availability information, same with hotels and car rental information. And all that information is flowing into a vector database, which is then providing the real-time context to your machine learning model and your chatbot to then respond to your customers. If you were to use a batch process to collect all this information from these flights and from hotels and car rentals about the availability and price of these services, and take a snapshot of that and pull it into a vector database every hour, imagine the experience you're providing your users. Let's say your latest snapshot is at 11 a.m. At 11:02, your user comes, queries for it, probably still gets relatively recent information. But somebody querying at 11:30 might not, especially and particularly during heavy seasons like travel, holiday season or summer vacations, when travel prices and hotel prices and availability can fluctuate dramatically on the order of a few minutes. So what you would end up with is a poor customer experience if you were to update your vector database at fixed batch intervals. And that would lead to like out-of-context information and poor customer experiences. So we've also established that machine learning and artificial intelligence use cases, especially the new ones, cannot be satisfactorily fulfilled with batch processing needs. We believe at AWS that there is a better way. And what is that better way? That's stream processing. Stream processing is just the act of collecting this data and aggregating it and processing it as it arrives, as opposed to taking batches at fixed intervals of time. Let's go back to our example of monitoring sensor readings. In this case, instead of now taking a snapshot every hour, storing this data, these readings in a localized database, and then taking a snapshot of that database every hour, you're piping this data into Kafka topics. Kafka, for those of you who may not be familiar, is one of the most popular data streaming technologies. It's open source, it's available today, and it's also provided as a managed service by AWS. Let's say you're storing this data into Kafka topics. Topics are these bin logs, and each record is written to Kafka as it arrives. And because Kafka can also make this data available right away for processing, you can process it right away, let's say using a Flink application to deliver results. Let's go back to our example of defect detection in this case. Let's say at time t equals to 1, an out-of-band reading arrives. It gets written to a Kafka topic right away almost, with some processing delay or network latency delay, rather. And because it's available in near real time, your Flink application can begin chugging along. And it processes it. And now because the size of the data is also small, you can finish test processing much faster than what you would if you, or at least much more economically, than you would have to process the entire batch. And now but most importantly, the result is available much, much faster. So now the end-to-end latency might be on the order of a few seconds as opposed to on the order of a few minutes or even tens of minutes. And the result is that your maintenance manager is a much more happier person than they were previously. So I think one key takeaway is that streaming does lead to faster insights, which batch processing doesn't. What about artificial intelligence and machine learning? That's an important use case. You still want to be able to do that. Does streaming help there? Let's take a look. Let's go back to our example of the chatbot. Now, instead of taking a snapshot at every hour and updating your vector database, which we sort of saw can result in out-of-context information, stale information for your users, and can lead to poor customer experiences, you're now taking each record as it comes. Each record has some information of flight prices, hotel prices, car prices, and availability. And each record is then committed to a topic is processed by that vector database right away and updated in a database, which can then result in near real-time information for your customers who are querying this chatbot for the latest flight and hotel availability. So safe to say that the modern artificial intelligence and machine learning capabilities, particularly generative AI ones, where you need real-time information, contextual information to keep your systems synchronized with the latest information, can help you provide better customer experiences that can obviously result in better customer value. So we've covered a lot so far. Let me take a step back and recap. So we started with the fact that data is changing. It's becoming far more diverse. It's becoming much more continuously produced. And as a result, there is a need to handle it differently. At the same time, business requirements are becoming much more stringent and much more demanding. Business executives, managers need this data right away to make faster decisions and better decisions to drive more business value as competition intensified. We also established that business batch systems are insufficient. It's good in certain places. It certainly still has a place in your data architecture, but it's not sufficient to do everything that you need to do with data today. And last but not the least, streaming can unlock value where batch systems previously could not. And in the next section of our presentation, Sophie, my co-presenter today, will walk you through some of the sample architectures, traditional architectures that exist today in batch systems, and show you how relatively straightforward it is to convert them into stream processing systems with minimal disruption and continue to deliver more value for your business. Sophie.
Thank you, Osama. Our session today. Before diving into the details of migration from batch to streaming, I would like to first look into starting point that may be familiar for many of us. So let's look at a typical batch processing, typical ETL pipeline for analytical system. I'm sure familiar for most of us, where we have multiple data sources, we have multiple databases, and we have a periodic batch processing, ETL, that extracts this data and then transforms this data by cleaning, filtering, enriching, and then loads the curated, the ready-to-use data into our data lake, data warehouses, or open source, for example, for creating really smart dashboards. But the problem is that those workloads, those data pipelines might take time. So doing only the extraction of data from our data sources can take time. It may take hours, but it also can take a day. And we also have tens and maybe even hundreds of periodic batch jobs that are running to curate our data on a hourly basis or minutes basis and so on. So end-to-end.
Sorry, you're running one slide behind. The next slide is the left one is the next slide.
Okay, thank you. Great. So we can see that the end-to-end time it may take for our system to get smart insights can be hours and even days. But the transform part is actually, in reality, is much more complex. Usually, we are implementing this transform part as a medallion architecture, meaning that we are incrementally improving our data while it flows from the bronze level to silver layer to gold layer. So such as at the bronze layer, we have a raw data, and then at the silver layer, we have more cleaned, filtered, enriched layer data, and then in gold layer is the data that is curated and ready to be queried. So end-to-end processing will actually depend on the time it will take to the longest chain of batch job to complete. And to be able to streamline our processing, to be able to react quickly, to be able to act on each event that is arriving, we want to process the data without stopping. We don't want to repeat the data, repeat the processing. So let's look at our basic components of streaming architecture, right? So actually, it quite resembles the architecture that you saw in our batch system. We have data that is streamed to our stream storage, right? Stream storage, consider it as a message broker, right, that can be ingested with high volumes of data, and the data is persistent for a duration of time. We need this persistency in order to be able for producers to produce the data in their own pace and for consumers to consume their data in their own pace. And if something happens to our consumers or producers, the data is not lost. So stream storage is Kafka or Kinesis. And first step is data that is being produced in streaming manner. The next step is data processing. We are continuously processing the data while it arrives. We are processing the data in motion. And comparing to our batch architecture, well, the data is processed after it was landed on S3 buckets. Continuous processing of the data occurs while we are receiving each event from our streaming storage. And the last component in our streaming architecture is our data destination, is writing the data into data store. We would like to write our data into the data store in order to maybe retain the data for a longer period, but also make the data available for further analytics, for example, by BI teams or maybe data analysts and so on. So as you can see here, the steps are really resemble to our batch processing architecture and to the ETL, extract, transform, and load. In this way, actually, when we are processing the data while it arrives, we can reach the end-to-end of near real-time experience. So, in the next slide, I will go into the details of each and every step of what we discussed before. Let's go first producing the data and storing the data into streaming storage. In the traditional databases, when we are extracting the data from operational databases, right, we are implementing different procedures of how the data is extracted. Usually, we may have snapshot procedures, we may have maybe queries or data pollers that are extracting the data in different intervals using different queries. And the way we are implementing those procedures is actually depend on the type of the database, right? So we have one procedure for MySQL database, one procedure for Postgres database. So it gets more and more complex, right? But the fact is we don't have only one database. We might have several database types. So we have more and more procedures and queries. And of course, we have many consumers. And each consumer might have its own conditions, how the data should be retrieved, with what formats it should be getting the data. So it gets more and more complicated. In streaming architecture, we would like to move actually from polling the data to a more event-based mode. We would like to react on every event that is coming from our database. So in order to produce the data in streaming mode, we have one option, just pushing the events by our application. Pushing the events, for example, from microservices and so on. And the second option, we want to use the CDC, capturing changes from a data store. And let's shift our focus for a moment just briefly to explain what is CDC. So CDC is actually a mechanism that monitors database transaction log. Each database, each OLTP database has a transactional sort of journal that records each and every operations that occurs on the database. So for example, we have insert, update, delete. All operations are registered to this transaction log. And CDC tool actually monitors this transaction log, and upon each event, it receives the event, transforms the event, captures and then sends the event to the destination. Kafka or managed Kafka or Kinesis. For CDC tool, you can use AWS Database Migration Service, AWS DMS, or you can use very popular open source library called Debezium. In this session, I will focus on sending the data to streaming storages like Kafka or Kinesis. But CDC tool is capable, of course, to take the data and store it in different databases, data warehouses, or even send it to data lake in Iceberg format. And if you're using Debezium, if you decided to go with Debezium, so the most popular deployment of this library is using Kafka connectors, Apache Kafka connectors. And with AWS, you can use Amazon MSK Connect and deploy Debezium with Amazon MSK Connect. The other option is to use Debezium as an embedded library. It means your application are actually just imports Java library and can use it to stream the data directly from the database into your application. So for example, Apache Flink CDC, Flink library does exactly that. And you can use this also with Amazon Managed Service for Apache Flink. And the last deployment options, less common, is to just use Debezium as a container, as a standalone application, and it will integrate with other streaming sources like Kinesis or even Pulsar and Redis. So by moving to CDC mode of work, we first achieved low latency because now we are reacting on every change that, that arrives to the system. We also reduced the load. We reduced the load because we have one CDC tool that extracts the data from our source database and push it to stream storage. And even if we have many consumers, all consumers can read the data from stream storage, Kinesis or Kafka. And also, we are now reading from transaction log and not directly accessing the database. And third, the architecture now looks more simpler, right? Because instead of implementing different scripts, different queries, we have one CDC tool that can connect to different databases. Okay, step number 2, processing data in motion. As I already mentioned, all the jobs running periodically take time. We do not want to stop processing the data. We want to process the data continuously. And for that, let's go back to our basic streaming architecture. For that, let's see what services we are going to use. So for producing and storing the data, we are using Debezium and DMS. For stream storage, Amazon MSK or Amazon Kinesis. For stream processing, managed service for Apache Flink. This is a good time to ask audience. I'm really curious, how many of you are familiar with Apache Flink? Can you please raise your hand? Oh, nice. Great. Awesome. Okay, so with Apache Flink, you can do smart processing. And just to recap, Apache Flink is widely adopted stream processing framework that is capable to process high volumes of bounded and unbounded data. It can process it in stream, but also in batch. But I think the superpower of Flink is being able to process the data in stream with stateful processing. So operations like doing a smart processing within a certain time of window, doing smart aggregation, doing event correlation, implementing maybe rule engine or CEP processing, complex event processing, this is stateful processing. But Flink can also do other tasks like doing filtering, data routing, data enrichment. And in fact, in one job, you can combine both stateful processing and stateless processing. And a few words about using Apache Flink with managed service for Apache Flink. with managed service for Apache Flink, you can use Apache Flink, and it is completely compatible with open source. You can leverage with managed Flink all expressive API that Apache Flink supports today, starting from high-level SQL language and then low-level streaming API in Java and Python, and you can use all languages and all APIs with Amazon Managed Service for Apache Flink, depending on your specific use case and the skills of your team. You can also use every connectors that Apache Flink community developed and part of open source Apache Flink. And actually, we just recently, AWS contributed 4 more new connectors to Apache Flink community. 1 connector for Kinesis data stream, 1 connector for DynamoDB streams, 1 connector for SQS, and connector for Prometheus. And not only, with Managed Flink and Apache Flink, you can implement your application using advanced time management features of Flink, such as handling late events, handling complex windowing, and Apache Flink has many options of implementing different windowing functions like session windows, dynamic windows, tumbling windows, and custom windows. And of course, leveraging Apache Flink capability of processing, stateful processing, and exactly once processing semantics. This is how Flink models its application. This is a sample data flow, a logical DAG directed acyclic graph of operators of every Flink job. And you can see here that we have 1 Flink job that can read from different Kafka topics. This is only a sample, right? But it kind of reminds the ETL processing that we discussed before. So each Flink job can read different Kafka topics, and it can join the data and then maybe filter and doing some enrichment and also aggregate data. But in practice, it can do even much more smarter operations, like even doing machine learning inferences. So the part of transformation is actually can shorten for you the process of processing the data. And we discussed before the medallion architecture. Now, with only using Flink, you can simplify those steps. And instead of maybe doing incremental processing, you can directly create the most curated data, and then write this data to the output. And the most curated data can be written to different outputs. Here, in example, we have data destination S3, and we have OpenSearch. So you can see that one Flink job can handle different tasks. All right, so step number 3, writing the data into data store. And we want to write the data into data store because we want to retain it for a longer period, but we also want to make this data available for additional, maybe additional processing analytics. But 1 second before, just to remind you that in typical data lake architecture, when handling mutable data sets in our batch systems, in many cases, those architectures actually relied on append-only or rewrite approach, which means if you are snapshotting your data, right, you are snapshotting the data periodically, you either creating a new version each time of your data, right, and you are appending new version of this data, or you just rewriting the entire data set. Another reason for using only append-only mode or rewrite is because traditional data storage format like Hive, for example, or just data warehouse are not very good with updating the data. But with streaming, this can become a problem because in streaming, you would like to reflect the changes right away. So consider application like recommendation engine, right? You want to be able to update user profiles immediately. So we do need to support the ability to update the data pretty soon, right? Pretty immediately. So let's talk about ingestion patterns, append versus upsert in streaming systems. Consider we do have table that represents IoT device that measures temperature in a room. So we have table with device ID, temperature, last update time, partitioned by device ID, and we're beginning to stream our events to the stream. From the left side, we have a simple append statement which is just insert SQL. And from the right side, we have upsert query that updates the data. If the data is found in the database, it will just update the rows that it found. And if data is not present, it will insert new rows. So we have append and upsert write modes in our example. Let's start ingesting events from our IoT device. Event number 1, room A, is inserted into the both tables. And then we are getting our second event, room B, also. This is a new event, so both tables are getting this event. Room A, this is an updated event, and to append mode table, we're inserting a new row, while in upsert write, we're just updating the existing row. Room C as well, this is a new event, we're just adding a new row. And last, another update to room A. So as you see, we have a long history of temperature in append table, and we have an updated and current status of our room temperatures in the upsert table, in the right side of our table. And let's see the differences between two modes. This will help you to choose the right update strategy. So with append only, you are capturing all your data changes. It means that you have the precise history. It means that you might be able to unlock new business use cases. For example, you now can maybe calculate trends over time of temperature in a room. So you have accurate history. And the write procedure is actually really simple. You're just inserting new rows. But if you would like to read your data and you would like to get the last accurate status of your temperature in a room, you will have to do a sort of merge operations before reading this data, and it makes the reading more complicated. In the upsert mode, we do reflect the latest status of our temperature in a room, but it's much more simple to query. We do not need to do any merge operations. And of course, we are losing our history. And another problem that might occur when you are updating the data is that you might have several records representing the same key, and you're updating these records into your database. You need to take maybe the last update of this database. You need probably to do decoupling. So the write method becomes much more complicated. And of course, there's a dilemma of efficiency. You want to get really good latency, so you want to update each and every row. But from the other side, if you want to get better performance, you should maybe do a micro-batching and collect several rows together and then update it. So it's a dilemma of efficiency versus latency. And the last point, you might create write amplification issue, which means that you might be updating the entire floor, entire rooms, and the data set that is updated is really, really large. So let's get back to our basic streaming architecture and continue with our services that enable each and every step. So we saw managed service for Apache Flink that can also write the data into the data store. And I would like to add another service, Amazon Data Firehose, which is a serverless, low-code, no-code, that allows you to ingest data to more than 17 destinations, different destinations, including Snowflake, including Apache Iceberg. This is a new feature. and other Redshift and other destinations. And I've also added Apache Iceberg, open table format for our data lake. And I've added Apache Iceberg because we do want to support these update operations. I'm also curious now, how many of you are familiar with Apache Iceberg? Can you raise your hand? Awesome, awesome, cool. Yeah, so Apache Iceberg becomes really, really popular. It involves very fast. And combination of Apache Iceberg with streaming is actually works great together. Not only because Apache Iceberg supports updates and upserts, but also because it supports schema evolution, it supports snapshot isolation, it has time travel, all the features that are super important in streaming systems. With Apache Iceberg, you can achieve high throughput ingestion of near real-time data, and then you can make your data available for instant query. And another feature of Apache Iceberg that really works good with streaming is Apache Iceberg provides two methods of update. It can update the data using merge on read strategy, or it can update the data using copy on write strategy. Updating data using merge on read strategy means that when you are updating the data, you are not rewriting any files while you are writing this data, you are just appending new files. It means that when you will read the data, you will have to combine all this data. So merge on read strategy is optimized for writing, and it will require for you to do more optimizations before reading, and when reading the data, it will merge the data upon reading. With copy on write, this strategy is more optimized for read performance. Use cases where most updates are collocated in the same table, same partitions, and it will be easier for you to rewrite the same data files. But not everything is perfect with streaming data to data lake, and this is not only common to Apache, this is not only specific to Apache Iceberg, but in general, when you are streaming your data to data lake, you are committing your changes very frequently, right? Because you want to reach low latency, and this might create many, many, many small files. And not only because maybe you have a high rate of commits, but also, for example, with Apache Iceberg, you are using merge on read update strategy, and you are creating many files. When you're creating many files, it means that your read performance might be impacted, and you will have to run table maintenance. And here's another caveat. When you are running table maintenance, like compacting those small files into the bigger files, you will have to run those maintenance tasks in the way that they will not interrupt your streaming jobs. Okay, and the last consideration when you are updating your data while streaming, this is the problem we discussed in upsert mode. When you have a couple of events in the same batch that have the same key, and you want to update them all. When you do this update, and it doesn't matter what is your data destination, it can be Iceberg, but it can be other data store, you might create a non-deterministic updates. What event we should take for the update? So you have to do an additional logic of sorting and taking the last update. All right. So we are covered all three steps of migrating from batch to streaming. We discussed the streaming way of ingesting the data. We discussed the processing and storing the data. And now let's see a sample diagram of sample architecture that combines all the services we discussed. So we have data sources like Amazon RDS, and we have Amazon EKS microservices that are running and pushing the data into stream storage. The RDS is actually producing for us CDC events that are intercepted by MSK Connect running with Debezium source connector. And those events are produced into Amazon MSK. Microservices are pushing the data directly using Kafka Produce API. The next step is Amazon Managed Service for Apache Flink that continuously processes the data in motion, filters, enriches, and doing some smart logic to produce smart insights and store those inserts into different destinations. And I mentioned before, Amazon Managed Flink can already producing you the most curated data. Maybe in the streaming architecture, we do not need a medallion approach anymore. Of course, everything depends on the use case. And with one Apache Flink application, we can write the data to Iceberg. We can also stream the data to OpenSearch for creating dashboards for business analytics, real-time dashboards. And another option is to just send events notification directly to our end users. OK, so Osama, would you like to join? So we have few takeaways.
Is my mic on? Hello? Can I get my mic on?
You're on.
Oh, yeah. So yeah, thanks, Sophie, for that. We'd just like to sort of like close the presentation with a couple of things. We wanted to share some takeaways. I know there was a lot of content that was shared today. I think 3 things, if you were to leave this room, we'd like you to take these 3 with you. There is a genuine need for producing real-time insights and synchronizing your systems with the data that your systems are producing 24/7. So streaming can help with that. Secondly, streaming can also satisfy latency-tolerant use cases. So not only are you able to generate real-time insights, it's not like you have to now maintain 2 parallel systems, one to do sort of the traditional BI reporting use cases, and then streaming for more real-time and generative AI use cases. You can continue to use streaming for both of those use cases, and some of the examples that Sophie shared demonstrate that well. But even if you have concerns about how mature streaming is, I think what AWS has done over the past 10 years or so, or actually 11 years now since Kinesis Data Streams has been launched and over the years have added capabilities, is that stream storage and processing and tools are becoming far more mature, cost-effective, and easy to use. So while, yes, in the past, these tools weren't capable of serving mission-critical workloads, serving tier 0 services, now they are being used by hundreds, if not thousands, of customers to serve some of these mission-critical workloads and tier 0 services. So not only are they good enough, but they're also now getting more mature and battle-tested as years go by. So with that, I think I'd like to sort of end with a quick call to action. If you can just flip. Yeah. Please continue to learn more. I understand this is just the tip of the iceberg. We have amazing sessions. A couple of them are mentioned here. Feel free to take a picture of that. But there are more as well. So browse through your catalog, look at what other opportunities there are to learn more about streaming technologies. I think the other most important use case is take this learning back to your teams and then identify where you can start implementing this, and maybe start implementing it small if you haven't already started. That's how we typically recommend customers adopt streaming, is that pick a use case that may not be the most critical breaking use case, and you can start small and then expand over time. And last but not the least, please take your cameras out. Take a look at these QR codes. This is where we have some workshops that you can sort of like get your hands dirty and experiment, even after you're back from reInvent, and you can experiment with some of these technologies hands-on. With that, next slide, please. We'd like to thank you, and I think we are a data-driven company, so we'd love if you can take the survey and let us know what you thought of the session, what you thought of the content, and give us feedback, because we really do take that feedback and hopefully improve on it for next year. Thank you so much.
Thank you.